When we look at the night sky, we see a glowing sphere of romanticized dust, but the moon is actually a freezing, boiling desert graveyard, and it might be our only realistic escape route off this planet. The Milky Way contains over 100 billion planets and moons, and it's tempting to dream of colonizing any of them. If we wanted to terraform a neighboring planet to sustain human life, our closest option is Venus. This diagram plots the orbit of our closest neighbor. The distance between Earth and Venus can reach 162 million miles. Traveling that expanse creates a logistical hurdle that our current technology cannot clear. But compare that to the moon. On average, the lunar surface is 240,000 miles away. It is a tiny fraction of the trip to Venus. A spaceflight this short makes moving heavy equipment possible. We can ship supplies, transport necessary machinery, and carry colonists at a cost that doesn't immediately bankrupt the mission. Humanity's path to the stars begins on this rock. We have to learn how to manipulate an ecosystem right here before we can look any further. Before we can settle the moon, we have to survive it. The environment is lethal because its atmosphere is impossibly thin. Instead of a thick blanket of air, the moon has what is known as a lunar exosphere. It's a paper-thin layer of gases that offers zero protection from the vacuum of space. This visualization shows the scale of the problem. A single cubic centimeter of the moon's exosphere contains just 100 molecules. That same space at sea level on Earth holds 100 billion molecules. Planting trees won't work in a vacuum like this. Creating a life-bearing ecosystem will require brute force planetary engineering to thicken the exosphere from nothing. To thicken the exosphere, we need a massive delivery of gas. Our best option is to drag 100 icy comets out of orbit and crash them directly into the lunar surface. When these massive chunks of ice hit the surface, they pulverize. The extreme heat of the collision instantly vaporizes the ice, populating the exosphere with a massive surplus of water vapor. That vapor provides two foundational elements for breathable air and biological growth: oxygen and hydrogen. This bombardment also addresses a physical limitation. Currently, the moon is tidally locked to Earth, forcing it into a sluggish 30-day rotation. Changing the rotation of a celestial body requires a staggering amount of energy. By directing these 100 comet impacts at precise angles, we can use them as kinetic hammers to break that tidal lock and spin the moon up to a 24-hour cycle. This shift lets future colonists harness renewable water and energy in a predictable day-night environment. Even with a faster spin, the moon lacks insulation. Without a dense atmosphere to trap heat, the surface is exposed to inescapable temperature extremes. This chart shows the fatal thermal swing. During the day at the equator, temperatures boil at 250 degrees Fahrenheit. At night, craters at the northern pole plunge to negative 410 degrees Fahrenheit, about 266 degrees colder than the coldest temperature ever recorded on Earth. Aerospace engineer Dandridge M. Cole proposed an aggressive chemical solution, importing and injecting massive quantities of ammonia gas into the lunar sky. This animation shows the ammonia acting as a dual-purpose weapon. It fills the exosphere with nitrogen while simultaneously trapping and reflecting heat from the sun to trigger an artificial greenhouse effect. This chemical injection is the only way to insulate the surface, transforming a deadly thermal wasteland into a protected, survivable bubble. This entire process is highly theoretical. We are engineering a world from scratch, where a single miscalculation at any stage results in total failure. We don't know if the lunar crust can handle the shock of 100 comet impacts without shattering, or if the ammonia will actually trigger a lasting greenhouse effect. There is also a biological threat we cannot engineer away. Low surface gravity may cause devastating damage to human bodies over several generations. These risks suggest the moon is unlikely to become a permanent, lifelong utopia for our species. The moon serves as a high-stakes sandbox, a proximity-based practice run where we can learn to terraform a larger ecosystem without stranding people millions of miles from home. If we master these violent forces to colonize our moon, we will establish the foundation for reaching every other corner of the solar system.